just saying that I'm going to start the recording so that now Dr. Popova can start the introduction. The floor is yours.
Okay, hello everybody. I'm very honored and happy that you found time for my students to present. These are undergraduate students from different areas. So actually this research started, similar research started in 2014, where Julia was one of the participants. At that time, she was an undergraduate. And Julia and some other people and me, we were investigating the symmetries in art, the connection between mathematics and art, going to museums and looking at the pictures of Escher and describing the symmetries in the plane. So my students were able to recognize the 17 possible structures in the plane, and they also wrote an algorithm of recognition. So 5 years later, when Julie is already a teacher, she approached me and she expressed a desire to continue the research of symmetrical structures and their applications, and actually symmetries are everywhere. Well, we did some work in 2D. What about 3D? So we are going into crystallography. And that is much more complicated. There are 230 structures and a lot is still unknown, of course. We started last year, around December, November, December, we were already 5 people, Emma, and Andrew and Pavel and Julie and me. So the other 3 are students now. They were students in my classes. And we decided to study the application of symmetric structures in virology, because that seemed really challenging. Although symmetrical structures are in molecules, as everybody knows, and even in dancing. But my students decided to look at the viruses. And this was even before COVID stroke. So we presented our first findings in February at the undergraduate symposium, Florida Undergraduate Research Symposium, end of February. And in March already, they began speaking about COVID. So we were proactive. We didn't know about COVID at that time, but it turned out to be really very, very challenging and interesting. So, of course, we 5 could not go very much further without knowing biology. So we made a call, and with the help of the undergraduate research office, we attracted 6 more people from biology and biochemistry. So now, at the moment, our research group consists of 10 undergraduate students, plus Julie and me. Julie is serving like my assistant, and all the rest are undergraduate students. And some of them are here in the audience. So if you have questions both ways, they're available at the end of the talk as well. Okay, so without further ado, Emma is a mathematics major, Andrew is a computer science major. We decided that they will talk today on behalf of everybody else about our first findings. So the floor is yours, Emma. You're muted.
Symmetry and quasi-symmetry and viral capsid structures. Andrew?
Alrighty, and I'm going to go ahead and just do a brief introduction. Dr. Popova already kind of mentioned a lot of this, but I do want to, just add to that and transition into our presentation. My name is Julia, by the way. Nice to meet you all. So About, yeah, I'd say 5-6 years ago when I was an undergraduate, I was really fascinated by group theory and algebra and how symmetry especially may apply to different aspects of, the real world. So I became especially fascinated with art at first. And there was fairly, simple applications of this when we were looking at the 2D plane. We became especially interested in 2D crystallographic groups. In particular, these are called wallpaper groups. These are, this more famous name for them. And we realized that there were 17 of them. And through this project that I had conducted as an undergraduate, we were able to prepare the building blocks for a computational algorithm that would classify these 2D crystallographic groups or wallpaper groups. So we started digging into the 3D crystallographic space groups, but because there are 230 of them, and obviously computational algorithms in 3D are much more complicated, the research kind of took a halt, but we've picked it up recently. And we've become especially interested with how this classification algorithm and the study of these groups could apply to the field of virology. And as Dr. Popova said, it's funny because we became fascinated with this before COVID had even been spoken of. So it just happened to coincide pretty nicely. But in the field of virology, viral capsid shells, which is the protein container that encapsulates a virus, tends to follow quasi-symmetric or symmetric arrangements in which the applications of group theory and topology in 3D will help to shed light on these viral structures. And a lot of the crystallographic studies that we had done in 2D are helping us build that background for the 3D. So through this project, as you can see in our last bullet, we do wish to explore further types of symmetric structure in order to better model viruses and aid in the development of better and more efficacious treatments.
Right, so just kind of an overview of the virus structure that's relevant here. So a virus is essentially a strand of RNA or DNA code encapsulated by a protein capsid cell. And because capsids are so small, only nanometers, typically 10 to 9, it allows the virus to sneak into a cell, and after deceiving their mechanisms, they start to replicate and infect the host. So the size and the structure of the capsid is dependent on the length of the RNA and DNA code. So they can get relatively large and complex, and though despite this, capsids still consist of simple protein building blocks because, again, the capsids are so small that only a limited amount of information can be efficiently encoded in the RNA or the DNA strands surrounded by the capsid. And so as a result, there are going to be, as a result of them consisting of relatively simple repeated protein building blocks, this allows for symmetries to become present and for us to search for patterns. All right. So many capsid protein shells can self-assemble or fold their proteins into virus-like particles, thus producing the structure of the virus themselves. Casper and Klug's work found that icosahedral group symmetry and geodistic symmetry are common among viruses and allow them to compact their genome. So symmetric groups, as an overview, describe the transformations that can be enacted upon objects possessing one or more forms of symmetry while occupying the same space in the same way. So for example, if you rotate it over a symmetry axis, it'll continue to occupy the space it did before in apparently the same manner that it did. Right. For an icosahedron specifically, its symmetry group is going to consist of 60 elements, order 60. These elements are comprised of 4 rotations about centers of 6 pairs of opposite faces. So if you take any 2 opposite faces, draw a line through them, you'll find that they have a 5-fold rotational symmetry. And this again is true for all 6 pairs of these faces, giving 25 5-fold rotational symmetry elements. And from there are also 2 rotations about each of 10 pairs of opposite vertices, giving us 23-fold 23-fold rotations. And there is 1 rotation about the centers of the 15 pairs of opposite edges. So that gives us 15 two-fold rotations. So again, together, these all with the identity element comprise the 60 elements of the icosahedron's symmetry group. So going from this model, since not all viruses are going to be a perfect icosahedron, it is still possible to approximate one using triangulation. So expanding upon this model, Casper and Klug generalized Buckminster-Fuller's architectural design principles to cover spiritual viruses using this triangulation of the icosahedron and they derived a formula which describes all the possible icosahedral quasi-equivalent structures. So this is going to be T equals B squared plus BC equals C squared. And what this T number gives us is going to be the number of subunits within each triangle that is used to create the quasi-symmetric icosahedral structure. Further, if we take 60 times T, this will give us the number of subunits that is present throughout the entire icosahedron.
Yeah, the number of proteins.
Yeah. So on a so when we're talking about a virus, this is each subunit is going to be one protein. Okay, Andrew. Thanks. So the Casper and Klug model solved many virus modeling issues, and however, there are a number of viruses, such as certain cancer-causing viruses, that were unable to be described by it due to the fact that they demonstrated five-fold pentagonal structures, which can't be constructed from equilateral triangles like in the previous models. So using Penrose's irregular kite and dark shapes, the plane can be tiled while displaying both reflectional and five-fold rotational symmetry, but not translational symmetry. So Penrose tilings are aperiodic, they never repeat themselves, and so they were actually a crucial part of modeling viruses like HPV, which Twalrock was able to do. Andrew? Okay. From there, we have, so the approaches that we've discussed so far give us information on the surface structure of these viruses. However, they don't give us any information about the tertiary structure or the thickness. And using affine extensions allows us to gain information on those. So Twalrock and Keefe were actually able to develop 41 points describing these extensions. You can see below in this image, there are 3 examples of the point groups. And again, they just provide greater insight and detail into its structure. Okay. And here you can see 2 examples of both helical and icosahedral structures for viruses. The first one, is a helical virus capsid. And as you can see, they have less volume for containing the RNA and the DNA inside of it, whereas the icosahedral structure allows for the maximal internal volume and is the most efficient way to construct the virate capsid space-wise. And it's a solid, again, an icosahedron is a solid with 20 faces. Each face has an equilateral triangle and which is used to approximate a spherical molecule, which is why viruses with an icosahedral structure are often described as spherical.
All right. So we also, my end, we researched the virus imaging methods. At first, until recently, X-ray crystallography was the best method for imaging viruses, but X-ray crystallography wasn't capable of imaging every single virus due to, I think, if it was wavy. If a virus was wavy, it wasn't able to create a crystal based off of the virus. So we looked more into cryo-EM, where cryo-EM images molecules by freezing them and sending an electron through them to capture a movie or multiple frames of the molecule. And this movie forms a composition of images in which a 3D model of the virus is created. This was super useful for me as a coder because I got to see how they recreated the virus, and it also helped us to see what they use to image viruses. The 3D models are created using multiple methods due to the structure of a virus. In icosahedral reconstruction, is electron crystallography and single particle reconstruction are used. These reconstructions take advantage of internal symmetry and repetition to generate a detailed 3D image from the dataset. In helical reconstruction, a repeating pattern of a helix is used to create the structure, as is pictured here with the Ebola virus. For the code, we worked off the previous research studies code of detecting wallpaper groups and art. We were still having trouble with detecting the unit cell, and that's what we are currently working on. But in implementing an algorithm to identify the symmetry of an object, the first step is analyzing the image or object in order to identify and create a lattice. And our current approach to doing so begins with autocorrelation and cross-correlation to detect and analyze the pattern, and from there, isolating the maxes and find the relative maximas. For the 2D code, we then are playing around with checking if the vectors we get from the peaks or maxes and maximas are collinear, and we are currently experimenting with that. And hopefully the 2D code will help give us more experience with detecting symmetry so that we could implement it properly on viruses in the future. But for now, we are attempting to work on it with things such as Escher's paintings, because they already have an established symmetry group and are able to test if our code is accurate. Do you want me to read this part, Emma?
Go ahead.
Okay. In the future, we would like to have every virus known be classified, tested, and modeled. By classifying these, the possible structures that a virus can take, we can help develop methods that inhibit these structural changes and prevent viral infections. We especially wish to continue studying the 3D Penrose tiling in more depth, as there is little pure mathematical research done on these algebraic and topological structures. So, to work on coronavirus, COVID-19 has a spherical protein shell, which is actually a viral envelope or membrane, together with the characteristic spike proteins. These spikes are not as rigid in symmetric positions as they would be in the context of a typical protein container, as would be the case in icosahedral viruses, which are the majority of viruses. The actual nucleocapsid, called nucleocapsid instead of capsid, as it is surrounded by the membrane that you are seeing from the outside, is helical. This fact contrasts the majority of viruses where the capsid is a spherical or cone shaped as in HIV. Such helical structures can be described by a combination of a rotation and translation using affine extensions similar to the affine extensions of the icosahedral group. So the findings of the French Department of Health: there's serious adverse events related to the use of non-steroidal anti-inflammatory drugs or have been reported in patients with COVID-19. COVID-19 gets into alveolus through the ACE2 receptor, and non-steroidal anti-inflammatory drugs increase expression of the ACE2, which makes it easier for the virus to get into alveoles and destroy them 5 times faster. The non-steroidal anti-inflammatory drugs should be banned from use when people have fever symptoms. Ibuprofen, for example, ibuprofen, epinephrine, neobuprofen, and more. The treatment of a badly tolerated fever or pain in the context of COVID-19 or any other respiratory viruses should be based on paracetamol without exceeding the dose of 60 mg per kg a day and 3 grams per day. Conversely, patients on corticosteroids or other immunosuppressants for a chronic pathology should not interrupt their treatment unless otherwise advised by the doctor who follows them for this pathology. Possible cure created. Russia's Federal Biomedical Agency on Saturday said it has developed a drug for the treatment of COVID-19 based on mefloquine, which is used to prevent or treat malaria. The treatment was developed taking Chinese and French experience into account. It added the drug with high selectivity, blocks the cytopathic effect of coronavirus in cell culture, inhibits its replication. The immunosuppressive effect of mefloquine prevents the activation of the inflammatory response caused by the virus. Adding macrolide antibiotics and synthetic penicillins not only prevents the formation of a secondary bacterial viral syndrome, but also increases the concentration antiviral agents in plasma and lungs. All right, and these are our references. And I think that's it.
All right, thank you for this the talk. Are there any questions? If you want to ask any question to the speakers, just unmute yourself and let us know.
I do have a question, if you don't mind.
Let's go ahead.
What software did you use to do those computations, to implement your algorithm? What software did you use?
Currently, we're working in Python and MATLAB.
Yeah, the previous code was in MATLAB. We have played around with Julia and Haskell, but none of us are experienced enough, so we have resorted to Python majoritively.
And machine learning recently, right?
Right.
I have a follow-up question, 2 follow-up questions. Actually, besides the Penrose tilings, in 3 dimensions, are you looking at any other possible means to map out the surface of a virus?
We're also looking into Archimedean tilings because especially when it comes to the quasi-equivalents, there are a lot of structures that go outside of just the icosahedral group. And so the thing that's interesting about the icosahedral group that we've discovered is that typically the Casper-Klug model only works for essentially a viral structure that has like an icosahedral net with a hexagonal lattice overlaid on that icosahedral net. However, not every virus fits this. I wish off the top of my head I knew of an exact name of one, but there are actually quite a few viruses that follow Archimedean tilings in 3D. So we're also looking into that.
One last comment. I mean, you said for the cure, you looked at Russia, but I think like recently, like in the past week or so, I think Pfizer, I don't know how accurate this is, but I heard Pfizer has a vaccine that is 90%, has 90% efficacy. So I don't know. I mean, yeah, this could be something to
yeah, Pfizer is the recent one, and the one Emma mentioned was from like March, when they just kind of like, were working, like just starting and everything. But yeah, Pfizer was like is the last one who apparently created some vaccine. It's still not confirmed.
Yeah, and based on what they're saying, like, I mean, in the news, it's probably the most accurate. I mean, the best means that they have right now. I mean, I don't know if that's accurate.
Yeah, of course, but we will not know until it gets like officially tested and applied. But I mean, yeah, Pfizer is the recent one, the most recent one. You're right.
Okay, that's all I have.
Let me just tell you about the other participants. Pavel just spoke. He was from the beginning. His major is biology, right? He was in my calculus class though. Then Karina is here. Karina is also a bio major, and Jacob is a math major. And as I said, there are more people who were not able to attend, but it's very interesting cooperation between the math and computer science majors together with the bio and biochemistry students. We have once a week a meeting, official meeting, all of us on Zoom, but in the weekend they meet in groups and they discuss their findings, and on Thursday they present their findings to everybody. So there is a cooperation between the bio majors and the math and computer science majors all the time. And that's how we are progressing. Actually, the first mathematician who was looking into viruses was Raidun Tvaruk. She's a professor from York, England. And she was the first who started this. And she's still working on it very actively, of course. Yeah, we are looking for further cooperations. We have visited a laboratory of Andrew Terentis, but his laboratory, of course, we could only see the structure of the molecules. The viruses are very, very tiny bastards. So we still want to establish cooperation, and we are on the way to establish cooperation with Max Planck Institute in Jupiter and visit their laboratories, because they have, of course, intensive research in biology. But I would like to ask if the other students have any questions. Karina, Jacob, do you want to add something about your research at the moment? Karina, probably. Hello?
Hi, yes. Yeah, as of now, indeed, the collaboration between math people and bio people is very interesting. And now we are starting to relate biology even closer to math. Since I don't have my presentation today, I wouldn't want to share our results, but of course now we're working on the triangulation numbers and RNA, how they work together, and how can we find symmetry by knowing the protein structure more in detail. And now we're actually starting to work with the chemical connections, so we can actually see and understand the symmetry even better at this point.
Mm-hmm. Yeah, it's an ongoing research. We're very excited, and let's see what happens.
All right, are there any other questions related to this talk? If not, then I will thank the speaker again, and thanks everybody.